So we have been talking about hypothesis testing. We went through and did the one proportion z-test. Okay, that was when we were testing a claim about a population proportion. And then we did a one mean t-test, and that was when we tested the claim mean. Friday and Monday.
But why Monday? Can we make it Tuesday?
So, we are now moving on to a two-sample z-test for proportions. Why do you think it is two-sample?
Because there's two samples.
Yeah, there's going to be two samples. And where do you think those two samples are going to come from?
Wasn't Gracie here?
Yeah, it's over there behind her.
Where do you think the two samples are going to come from? Where are we going to get the two samples? From the two different populations that we're going to be looking at. So, here's what we're going to do. For state, we will test at alpha equals whatever the significance level. You're going to use 0.05 unless otherwise stated. The null hypothesis is going to be that P1 equals P2. So the null hypothesis is going to be that P1 equals P2, which basically what that means, we've got two different populations. And we are going to assume that they have the same proportion of whatever it is we're looking at. Same proportion of people who take the SAT. Same proportion of redheads. Same proportion of boys. Same proportion of people who drive trucks. Whatever it is we're looking at, okay? We're going to assume these two different populations. Maybe we're going to do McKinney High versus McKinney Boyd. We're going to assume that those two different populations have the same proportion of whatever it is we're looking at. That's going to be the null hypothesis, the assumption, okay? But we're going to have a suspicion. The suspicion is probably going to be that one of them is greater than the other, or maybe it'll be that we don't know how, but we just think that they're different, so that they're not equal to each other. We're going to define our parameters, and we're going to have to define them both. We're going to check all of our conditions, and we have to check the conditions for both. When we get to normal, that means we're going to have to check the conditions for all of the things. We have to check the conditions for all of the things. Okay? Got it? Okay. And then we're going to say that our sampling distribution of p hat 1 minus p hat 2 is approximately normal. Okay. Okay. Now, we're going to use a 2-prop z test. 2-prop z test. This is going to be under stat test 6 in your calculator. We're going to plug in all the stuff, and then the calculator is going to give us the z test statistic and the p-value. And that will tell us how far in standard units our sample's difference was from what it should have been, assuming that they were 0. And the p-value, the probability of getting that from sampling variability. And then your conclusion, you guys, it's going to look exactly like you have been doing your conclusions for significance tests. All right. I do want to point out that you may see your hypotheses written slightly different. You may see, instead of seeing P1 equals P2, you may see P1 minus P2 equals 0. Either one of those is a perfectly acceptable null hypothesis. They are exactly equivalent to each other. Do y'all see how those are exactly equivalent to each other? If I were to subtract P2 from both sides, that is how I get P1 minus P2 equals 0. Because this P2 would cancel on that side and leave nothing or a 0. Think of it this way as well. Let's say the proportion in the first population is equal to the proportion in the second population. then what is the difference in their proportions? 0. If they have the same proportions, then their difference would be 0. So that's why these are equivalent. Okay? Again, we are going to get our z-test statistic, which is going to tell how far and in which direction the sample is from the mean of the distribution. We're going to get our p-value, which is the area that is as extreme or more extreme. And this is how the z-test statistic is calculated. This is the value of the sample, p hat 1 minus p hat 2, minus the mean of the hypothesized distribution. Now, most of the time, or actually all of the time, in these particular problems where we're assuming that they are equal to each other, that hypothesized value is going to be 0. The hypothesized value would be 0 because it's hypothesized that they have a difference of nothing. We're hypothesizing that they are the same, so they have a difference of nothing. And then the bottom is the standard deviation or the standard error. And so that's where we get the z-test statistic. Value of the sample minus the mean of the hypothesized distribution divided by the standard deviation of the distribution. So that's where all the numbers come from. But you guys know, just like we've been doing, we're going to use the calculator to get most of this. The calculator is going to calculate the z-test statistic for you and do all the things for you. All right, so again, just to make sure you got it, this is a 2-prop z-test. The null hypothesis will either be P1 equals P2 or P1 minus P2 equals 0. It will be one of those formats. The alternative, it will depend on what your suspicion is. Do you think that population 1 has a bigger proportion than population 2, smaller proportion, or that they're just not equal to? Okay, the z-test statistic, I'm not going to rewrite the formula. You guys saw it on the front, so you could say C front right there. Okay, the p-value. So let's say that our alternative hypothesis is that P1 is greater than P2. That means that I think that the proportion in the first population is bigger than the proportion in the second population. So when I look at their difference, I would get a positive number. If I think P1 is bigger than P2, then I would get a positive number anytime I'm looking at their difference. The null hypothesis says that your P1 equals P2 and that there's a difference of 0. That's where the null hypothesis is, right there in the middle. And so in this situation, the only way that I'm going to prove my alternative is if I get evidence that P1 is really bigger than P2 by finding that the sample of P1 minus the sample from P2 is, in fact, greater than 0. So my evidence can only come from the right side of the middle. And the area that would be as extreme or more extreme than that particular sample, just because the sampling variability, is called? What's that area? That's the p-value. Very good. Now, let's say that I have a suspicion that P1 is less than P2. In that situation, if P1 is less than P2, then when I look at their differences, I would get a number that's less than 0. I would get a negative number. That means that my evidence would be under the claimed value of 0. And now my p hat 1 minus p hat 2, because p hat 1 would have been less than p hat 2, now I have a negative, and my p-value is the area as extreme or more extreme than that. That would be the p-value. And finally, sometimes I might just think, well, I don't know how they're different, I just think they're different. So therefore, their difference is not 0. In that situation, we can get evidence from either side, either above or below, it doesn't matter. And that would be our picture of that. Cool? All right, let's do an example. Whee! The Pew Research Center recently selected a random sample of 269 18 to 29-year-olds and found that 59% of them use Instagram. A separate random sample of 401 30 to 49-year-olds found that 31% of them use Instagram. So we have two populations. What are the two different populations? The different ages. Okay, cool. We took different sample sizes from each, and that's fine. Now, in the 18 to 29-year-old group, 59% of them were using Instagram. In the 30 to 49-year-old group, 31% of them were using Instagram. Does it look like there's a difference between these two? Yeah. But is that sampling variability, or is there really a difference? That's what we're going to find out. Do these data give convincing evidence that a greater proportion of 18 to 29-year-olds use Instagram than the 30 to 49-year-olds at a 5% significance level? State. How do we start this off? We will test. Very good. We will test at alpha equals 0.05. My null hypothesis is that P1 equals P2. That's always your null hypothesis in a two-proportion z-test. Now, the alternative. What direction am I thinking for the alternative here?
1's greater than 2.
Very good. We're thinking that P1 is greater than P2. Now, that is only going to be true if I define P1 as the 18 to 29-year-old group. So we're going to say P1 is the true proportion of 18 to 29-year-olds on Insta.
Why are we defining P1 and not just P?
Because there's two P's.
Do we need to define P2 as well or no?
And now we're going to define P2. P2 is the true proportion of 30 to 49-year-olds on Insta. Okay. We have clearly defined our parameters, and we've got our null and alternative hypothesis. I do want to make sure that you guys see this, that this could have been the null hypothesis, P1 minus P2 equals 0, and my alternative would have been P1 minus P2 is greater than 0. Either one can be used. You can use whichever one you want when you are doing your hypothesis tests. But you do need to be able to at least recognize both of them in case of a multiple choice type question. Okay? All right, what's next? We stated. Now what? Yeah! Let's plan. Time to plan. Y'all sound so excited about planning. Plan. Random. We have an SRS of 269 18 to 29-year-olds. And we have an SRS of 401 30 to 49-year-olds. So our random condition is met. Now what? Independent. 10 times our first sample size has to be less than our first population size. 10 times 269 is 2,690. Do you think that that is less than the population of 18 to 29-year-olds? Okay. Ten times the second sample size has to be less than the second population size. So 10 times 401, that's 4,010. That has to be less than the population of 30 to 49-year-olds. You think that's okay? Probably fine. Probably fine. And now what are we going to do? Normal. Let's check normal. We need to make sure that N1 times P hat 1. We are going to use P hat here. Here's why. There is no hypothesized value. Okay, so there's not a P naught here. If we had a P naught, it would be 0, meaning that their difference would be 0. But we're not saying that we think the proportion of them both is 50% or whatever. We're just saying we think that they're the same or one is bigger than the other. So N1 was 269. P hat 1 was 59%. So there was 59% of this sample said that they used Instagram. Now, if I multiply these, I will get the number of successes in the sample, the number of Instagram users in the sample. But when I multiply these, I get a decimal. What do we get?
158.71.
158.71. Can I have a number of successes, a number of Instagram users that is a decimal? No, so I need to round this to 159. That is my number of successes. That is my number of Instagram users in the first samples, in the first population sample. So there were 159 Instagram users in the 18 to 29-year-old group. N1, 1 minus P hat 1, 269 times 0.41, that is 110. That means there was 110 failures, failure being not using Instagram. Now we're going to check N2 P hat 2. 401 times 0.31. What is 401 times 0.31?
Oh,
31. So, can I have that as my number of successes? No, I cannot. So what do I do? 124. There were 124 30 to 49-year-olds that were using Instagram in the sample. So now I do N2 1 minus P hat 2. 401 times 0.69. 277. 277 failures not using Instagram in the 30 to 49-year-old group. Are we done with normal? No. What do we got to do? We need to say that all of these are greater than or equal to what? Not 30. 10. For large count condition for proportions, it's 10. And then we need to say the sampling distribution of P hat 1 minus P hat 2 is approximately normal. Dun, da, da, da. All of the conditions are met, folks. Aren't you excited? And so now what do? Now we're going to do the do. Let's do it. Do. We are going to use a 2 prop z-test. We're going to use a 2-prop z-test. This can be found under stat test 6.
You said sampling distribution of P1.
P hat 1 minus P hat 2 is approximately normal. Stat test 2. I mean 6, sorry. Stat test 6. Stat test 6. Stat test 6. Stat test 6. Stat test 6.
Do you have to put user or use?
2-prop z-test? 2-prop z-test?
Do you have to put user or just?
You can say 2-prop z-test. That's fine.
Wait, was X1 the?
All right, X1. What does X1 stand for? The number of successes from the first sample. This, ladies and gentlemen, has to be an integer. If you put in the decimal, you will get an error because your calculator wants it to be a number of successes, and you cannot have partial success. So how much are you going to put in here? 159. N1. What is the sample size of the first? Was N1? 269. What is X2? The successes in the second sample. 124. And N2.
401.
All right, now,
Greater than P2.
this is why I personally prefer the how is P1 related to P2 in my hypothesis, is because your calculator wants to know how do you say in your alternative that P1 is related to P2. And in fact, we are saying that we think P1 is greater than P2. So we would need to select that one. That's why I prefer that, but you are welcome to use the other one if you want.
How do we even have a decimal number of successes?
You can't.
Well, no, but like if they gave us the information and there is a decimal, like how does that work?
Which one's actually the P-value?
Yeah, pretty much, yeah.
Just John on the side of those.
Says what?
Oh, no, that's just scroll.
Oh, okay. All right. All righty. So, ladies and gentlemen, please select calculate. If you do calculate, you will get the z-test statistic. Now, again, I want to remind you of what this z-test statistic is telling you guys, okay? We have a distribution of p hat 1 minus p hat 2. And in that particular distribution, we assume that P1 equals P2, and therefore their difference is 0. But we took a sample from each of those populations, and we found their difference. And how far away from them being the same is our sample? That would be our z-test statistic. How many standard units is our sample from being the same? 7.24 standard units. 1, 2, 3, 4, 5, 6, 7. Wow! That's how far away our sample difference is from being the same. This is where p hat 1 minus p hat 2 is found. Way over there. And the area, the probability that that difference is from sampling variability. That's the p-value. And that number can be found right underneath your z. What is your p-value? What's the probability that this was all just a little bit sampling variability?
Oh, you want
2.25?
548. Sure.
So, y'all are telling me the probability that I get a sample difference this far from what it should be is 225%?
Yes.
It has an e to the negative 13 at the end.
Did you see it has an e to the negative 13? Is that important?
Yeah.
A little bit. Y'all should be able to look at this and see that there is a very, very small chance that this was just a sampling variability thing. We have pretty clear and convincing evidence that there is a true difference between these two proportions. Okay, and in fact that P1 is greater than P2. So there's my p-value. It's teeny tiny, super duper little bitty small. Essentially, there's no chance that this was sampling variability. Essentially, this is telling you that you have all the evidence you need to say for sure that the true proportion of P1 is greater than P2. All right, what's the first word of the conclusion statement for any hypothesis test we do? P-value. P-value equals 2.25 times 10 to the negative 13th. How does that relate to the alpha? It's just a little bit smaller, 0.05. And so what do we do when our p-value is low? We are rejecting this hoe. Ladies and gentlemen, there is convincing evidence, like real convincing. There is convincing evidence that the true proportion of 18 to 29-year-olds on Insta is greater than the true proportion of 30 to 49-year-olds on Insta. And yes, there is a chance that we made an error. What type of error might we have made? Because we rejected the null hypothesis, what type of error is possible? Type 1.
It's like, can you give us more room on these? Like, I need a whole page. I write too big.
I'm sorry.
My conclusion's always very smushed.
I'm so sorry. Since we rejected the null hypothesis, we may have made a type 1 error. Now, what's the big deal here? So we said that the true proportion of the younger kids is greater than the true proportion of the older kids. What's the big deal? What's the consequence of that?
Nothing.
It's just misinformation, okay? All right, so we said P1 is greater than P2, but it's not. Now, there was very little chance that this was sampling variability, but what's the probability that we made a type 1 error? Very good. The probability of type 1 error is literally just alpha, and in this particular problem, that was 0.05.
Yeah, that almost got me the other day.
Yeah,
Significance first, because the significance is equal to alpha.
yes.
I thought it was 1 minus significance, or 1 minus significance. I thought that was equal to alpha, but I got like 0.95 or something like that. And I was like, I really don't think that makes sense.
All right, what do y'all think? Do you have any questions about this?
I think the law of cosine is easier.
You think?
Yes.
Okay.